So last talk of the day, we're very happy to have Stephane Mallat from the Collège de France and the Flatiron Institute to tell us about diffusion.
Okay, well, thanks, and that's great to be after Petros, who've outlined the whole field. So I'll be much more narrow and just look at two problems, but which are directly related to what he has been speaking about. The only thing is that it will be the opposite. I'm not going to look at all at dynamics, but at system at equilibrium. And things are much easier if you have a system at equilibrium, of course. Then the whole system, if you want to learn the physics, is about learning the probability distribution, which is defined by the Gibbs energy here of the system. And of course, the challenge is whether we can or not, or under what condition can we learn the Gibbs energy given a limited number of samples xi of the probability distribution. And a priori, we well know that this is not going to be feasible in very wide condition because of the curse of dimensionality, but in the case of physics, you have the equations. Okay, so there are these well-known problems such as the cosmic web, such as turbulence, where we have amazing results, such as the one that Petros has shown. One question is still to understand why. How come we can build such models? There was this question essentially was raised by Kolmogorov in the 1940s. What are the properties of the probability distributions of turbulences? Now, what we are now doing in machine learning seems much more complicated since we are generating very complex images which has absolutely no ergodicity or stationarity properties. And these are just examples of faces. And when you look at such image, the kind of question which immediately arises, are we really sampling a probability distribution, or are we just essentially memorizing? Are we taking our database and are we rebuilding a face by putting some kind of patches of the original image? And that seems very likely that's the kind of thing that's happening. It's exactly the same kind of question that one may ask on ChatGPT. Is ChatGPT really generalizing or getting data out of the database and basically doing some basic manipulation out of them? So that will be the first questions that I'll be asking and trying to address. And the second question is what kind of structures allows us to go around the curse of dimensionality? So these will be the two parts of the talk. The first part is about this generalization question. Is it generalizing or is it memorizing? And then we'll look a bit in the deep neural network structures, and I'll do the relation with statistical physics, showing that one key element to go around the curse of dimensionality is indeed scale that Petros mentioned. And behind scale, you have the renormalisation group in physics, and we'll see that it proceeds in very similar way. So one key idea that we find in all these algorithms is that one very effective strategy to model complex probability distribution is to use a transport. So how do you build this transport? You take your probability distribution, you simplify it by putting a first transport that may, for example, lead here to a Gaussian, and then you try to invert this transport. And if you can indeed invert this transport, then you can sample your Gaussian, and by running the inverse transport, it will lead to a sample of P of X. But then the question is what kind of transport you can build such that the inverse can be actually computed. Okay, and so a priori, the simplest kind of transport is to follow some kind of group transformations, and we'll look at two approaches to do so. The first one is score diffusion that was briefly described by Petros, which amounts to use the noise variance. These are the standard now image generation. And the second transport we'll look at is the transport used in the renormalisation group. In other words, it's the transport across scale. But key ideas are quite similar behind these two. Okay, so let me come back to what Petros described very quickly in a slightly slower rhythm. So how does this score diffusion algorithm work? The transport that is being used is the Ornstein-Uhlenbeck equation. So basically what you do is you progressively add noise over the image until the point it's going to be totally buried and below the noise. Now, then you invert this equation. This is a stochastic PD which can be inverted, but the term, which is the drift term that is going to appear in the stochastic PD, is the score, in other words, the log of the gradient of the log of the probability. Now, this is a result that is known quite well, but a priori, nobody expected that one could estimate this gradient of the log probability. And that's the remarkable work of Yan Song and his collaborators, who showed that effectively you can indeed learn this gradient of log probability, this score, with a deep neural network. And the idea is based on a simple equation that has been proved several times in the 50s, 60s, 20s, Rabbit, Maezawa, who observed that if you want to compute a denoising problem, in other words, you take a data which has been noised by adding Gaussian white noise, and you want to build the estimator X hat, which is as close as possible to the original data. So if you want to find the optimal estimator, the only thing that you have to do is essentially to move in the direction of the gradient of the log probability. So it's like a gradient descent. You move in order to maximize your log probability, but in one step you can do it. And this is a 3-line proof with an integration by part. Now, the result of that is that you can compute the score by essentially finding an estimator which minimizes the mean square error, which you can implement with, for example, a deep network. And if you optimize your deep network and by miracle you indeed get the optimal estimator, then you know that the score is just going to be the normalized difference between the estimator and the noisy signal. So that's what is being done. And does it work? Why? If you look at images, it's indeed very impressive. These are images of bedrooms, for example. So the question is, again, is it just a memorization or is it really a sampling of a probability distribution? So I'm only here going to look at the problem of variance. I'm only going to look at this question of memorization in this one. This is the kind of network that we are using, which have been using by almost everybody, a UNet. So observe here that you have a scale parameter. The image is progressively downsampled. And then to do the denoising, you have a progressive resynthesis at each scale. In other words, the data at each scale is being denoised progressively. So here's the experiments that we're going to do. You take your database, you separate it into 2 disjoint sets of images, okay? And you are going to train a first network from one set and a second network from the other set. Then you begin from the same white noise and you compute the transport with your 2 networks, okay? And you look at the image which is synthesized. So here the 2 set has only 1 image, and here are the 2 images generated from the same white noise. Now you can look in your database if these images do exist by finding the closest one. And it's not a surprise if you have a single image, the only thing that you do is you memorize. Okay, now you can take 10 images. You have 10 images. These are the 2 images reconstructed from the white noise. You can look in your database, boom, this image was in your database. 100 image, you do the same thing, it memorized. These are the 2 images synthesized, they were in fact in the database. 1,000 image, you again do the same thing, and again, you see that essentially you have the same thing in the database. 10,000 image, quality of the image degrades, but you essentially have an image in the database, and these 2 images are different. 100,000 image, boom, something different happens. The two networks are reconstructing essentially the same image. This means that they indeed learn the transport, which is now nearly independent from the samples that were used in the trained image. And if you indeed look in your database what are the closest image, they are totally different. What that means is that now the estimation has a variance which has gone to a very small stage. In other words, it is really generalizing. That means that you are really sampling a probability distribution. You can now do that on many different images, and it's interesting to look. So these are images which have been reconstructed from totally different sets, but that were extracted from the same training set randomly. And you can see that they are essentially the same, but they can be instabilities. You can see that, boom, suddenly a small error, you can have a glass that comes in. This comes from the instabilities of the dynamics of the inverse dynamics that can come in. Can do that on different things like bedrooms. And the transition essentially, if you have the same size network, happens about the same place. And you can see that it generalized after 100,000, whereas before it essentially memorized. At one point, it begins to do patches, and then it's generalized. One important point is that you see generalized with 100,000 images, only an image that we had were only 80 by 80. When you begin to increase the size of the image, this increases a lot. That means that, yes, these algorithms generalize, but you really need a lot of data to do so. And so that's the number n of generalization.
Is there a scaling factor or anything?
Okay, that's a very interesting question. You need to have a lot of computation power to study that in order to so we did that on, and that's the work that was done by Zara Zatokai, Florentin Gut, Eero Simoncelli together. And we did that on two cases, and we observed a kind of, but you know, with 2 points, it's always linear. So it was linear. You have 2 points, you have a straight line. But we increased the size of the network by a factor 10, and the images were about 10 times bigger, and we needed about 10 times more sample. So it does increase with the size of the image, but these are much more complicated than physics, and I'll come back to that. Okay, so let's come back now to the question of why can we indeed estimate such a random process, and it generalized, but what kind of random process are well approximated by such structure and neural network? So that requires to open the black box. And one question is whether we can build, in case of physics application, models with much fewer examples than what I have been showing in the case of faces or bedrooms. So let's observe again that you have one very important parameter in this architecture is scale. And that's what I'm going to speak about. So the question will be, when you have very complex geometry like the one that has been shown for turbulence, can we build models of such thing which are not total black box as what you would get with a deep neural network? So the observation essentially is old. This is the observation that was done by Kadanoff and Wilson, is that if you want to analyze the probability distribution of a microscopic, of a physical field at a macroscopic scale, one way to analyze its property is to look at the evolution of the probability distribution across scale. How do you do that? You average subsample, so you are progressively reducing the size here of the field. And at each scale, you are going to have a probability distribution, which is going to evolve. Now, you can relate the probability distribution at fine scale from the probability distribution at a coarse scale. And at fine scale, you will get it from coarse scale by, of course, multiplying by the conditional probability of xj minus 1 given xj. What are we doing here? And I should have presented that way. What we're going to do, if you think of it in physics, you are given the energy and you want to analyze the property of the energy across scale. In the case of data science, you are not given the energy, you are given data. And what you would like is to build a model of P. So what we're going to do is exactly the inverse transport that I previously mentioned. We're going to begin from the very small dimension probability distribution and progressively go upscale up to the fine scale and get a model of P. And to go from coarse scale to fine scale, we compute the probability distribution at fine scale from the probability distribution of coarse scale by multiplying by this conditional probability distribution. So this is the work done with Biroli, Etienne Blanqueur, Thierry Marchand, and Misaki Ozawa. Now, the key observation is the one of Wilson. The key observation is that this kind of strategy makes sense because this probability distribution may be very complicated, but the conditional probability distribution is much simpler. What is the conditional probability distribution? Is again the distribution of fine given coarse scale. And what we're going to do is to analyze this conditional probability distribution and to see how one can model this distribution. Okay, again, this is essentially ideas that were developed by Wilson and then refined in statistical physics. It's interesting because in physics, for the last 30 years, essentially the Fourier transform has been used to analyze the evolution across scales. Now, in the first paper of Wilson, it was not the Fourier transform, it was a wavelet transform. What does it mean? If you want to go from a fine scale, this is a fine scale image, to a coarse scale image, what you are lacking are the high frequencies. The high frequencies, you can represent them in a Fourier domain, or you can represent it in a wavelet basis. What is a wavelet basis? Essentially, it's a basis of waves which are localized. They have different orientation, but they are localized in space. So the high frequencies, you're going to represent them as inner product, which you can rewrite it as a convolution products, with the three wavelets. And this decomposition, if you choose well your wavelet, is an orthogonal decomposition. So you decompose it into wavelet coefficient in three directions. Positive coefficients are big coefficients shown in white. Negative, that corresponds to the wavelet near the transition. Wherever the image is regular, the wavelet coefficient are essentially zero because the contrast calculated by the wavelet is nearly zero. Now, the conditional probability of fine scale given coarse scale is the same thing now that the conditional probability of the high frequencies given the coarse frequency. So the whole question is to compute these conditional probability distribution. Now you can go to the next scale. That means that you take this low frequency, you sub-decompose it into wavelet coefficients, and you see now that these transition probability from one scale to the other is equivalent to looking at the correlation structure or the conditional probability between fine and coarser scale wavelet coefficients. So what I'm going to show is that in problems such as turbulence, you can indeed build models of these conditional probability distribution. And you can build relatively simple models, which are exponential models. In other words, the log probability is a linear function of that. Okay, so if I summarize, the idea is that the probability distribution, I'm going to decompose it in a very coarse scale, and then all the transition probability, and then build a model of all transition probabilities. To sample, essentially, you need to sample the coarse scale and then propagate. So you sample the wavelet coefficient from the conditional probability given the coarse scale, you go to the next scale. You sample given the coarse scale, you go, and so on. Okay? That's like the right branch of the units that we're doing here. Now, how to model this dependency? This is the fine scale image, the coarsest scale, and these are wavelet coefficients, but I show as complex coefficients. I do the same thing at different scale. Now, if you look at these images with this very geometric structure, you can see that they are very strongly dependent. You can see the same geometry in all directions, in all scale. However, if you compute the correlation between these images, the linear correlation is 0. Why is it 0? It's 0 because if your image is randomly translated, it's stationary. Your wavelet lives in 2 different frequency bands. So a stationary process is diagonalized in Fourier, the covariance. Therefore, 0 correlation across scales. And that's the big difficulty that you are constantly having when you want to model multiscale processes. You want to understand the dependency across scale, but this dependency is totally nonlinear. How can you build this dependency? You exactly do the kind of thing that neural nets are doing. You are killing the phase. You kill the change of sign. You can do it with a ReLU, or if you are in complex, you can do it with a modulus. If you do that, then these correlations are not 0 anymore. You've taken the absolute value, you kill the oscillations which created this 0 correlation, and now these correlation matrices are totally non-zero. But they are very large. Now you have very long-range dependencies, and to not take too much time, what you then need is to relocalize these dependencies. See, one of the very impressive things done by the neural nets and convolution networks is that all the convolutions are local. They are basically 3 by 3, 5 by 5. That means that progressively it relocalizes all the dependencies. The claim is that here, the relocalization is done by recomputing a multiscale transform stage by stage, which we're doing here. So the only coefficients we're going now to keep are the correlations of the wavelet transform of the modulus at the same location. So the number of coefficients we're going to keep, if you have an image of size D, is going to be of the order of log dq. So it's going to be very small. So essentially, that's what you do. You take your image, you do the wavelet transform, you apply your nonlinearity, which consists in taking the modulus, and then you reapply a wavelet transform. You normalize. That's exactly like in the renormalisation group in order to avoid having singularities which explode. You compute the covariance, and that's what you use to define your model. And you get an exponential. So this is the kind of example we've been working on. So much simpler than Petros has been showing. It's in 2D and static. So these are samples of 4 different physical processes. These are the samples generated with that kind of model. The difference with what I showed previously is that the previous model for faces had 7 million parameters, and there were images of 80 by 80. These are images of 256 by 256, and they have 500 parameters. So it's considerably reduced, which means that, of course, you can learn with much, much fewer examples, and you can check the statistics, the bispectrum, trispectrum, and so on. So what that means? That means that there is a lot of structure within these neural network computations. It's not surprising, otherwise they wouldn't be able to learn. But probably one of the main reasons why we can avoid this curse of dimensionality is really the hierarchical structure across scale. And there are, as I tried to show, very interesting connections with renormalisation group. This is just an example on circle. I'm showing it because to do the proof that you can capture the geometry just from these coefficients, if you have a random process which are just circle of arbitrary size, arbitrary position, is not an obvious thing. Because if you think about it, the geometry here is not at all captured by the structure of the contour or anything which is long-range correlation, especially. Everything is captured by a multiscale relation from very coarse to fine scale, and which produce a circle at the end. Okay, so the conclusion is, yes, it generalizes, but you need a lot of sample. And it's interesting to see, I'm not always sure that the experiment done in physics with these kind of algorithms are in the generalization region. That's something probably to check number of cases. And learning the geometry of complex physics seems to be possible with much fewer parameters than what is done in neural network. And I think there is a lot of very interesting things to do here in order to make these techniques interpretable for physics. Right now we have this huge network, but it's very hard to understand what it's really doing. And there are interesting topics at this interface. So let me again mention my collaborator, Thierry Marchand, Misaki Ozawa. Giulio Biroli is really the physicist with Misaki Ozawa, and Erwan Ali, Rudy Morev, and Brice Ménard. Thanks very much.